Okay, welcome to my channel. Today we're gonna talk about Compton scattering, the particle wave duality, and some about the double slit experiments. So we're gonna start off with Compton scattering. This was an experiment done by Compton, where he ejects a photon light beam to an electron. Suppose you have an electron here. So he shoots a light beam in, and he saw that after this initial frame, the next frame, the electron changes direction from stationary to moving like this. Electron and the photon changes direction and wavelength as well. So I will write it as gamma prime. So you can see that this is completely different from what Thomson get from his experiments. Thomson scattering. When Thomson does it, he sends in a light beam, but the electron doesn't change direction. It only shakes for a little bit, and the outcome, the light out, has the same wavelength. Well, why is that, you might ask? Well, that is because he used a low energy light. So his light beam has much lower energy than the rest mass of a particle, like we discovered. We discussed last time. And from this, he derived a formula, which is the finalized wavelength would be the initial wavelength minus HMEC 1 minus cosine theta. So this indicates that there is a loss in energy, therefore there is an increase in wavelength. So we can safely say that the wavelength, the final wavelength, is bigger than the initial wavelength. And well, you can see this in a graph as well, the famous two humps. It looks like a camel. So you have this, it's like a hump, increase in frequency. This. So this is the initial wavelength. Sum the I. This is the final wavelength, or the wavelength out would be greater than that. And how you get this graph is that you send in a light beam to a polarizer of sorts, so that it bounces off. And depends on the angle, you would get different outcome. But all the time, the final wavelength would always be greater than the initial wavelength. So you send in a light beam. You send in a light beam, and let's say that it bounces off at 90 degrees sharp. This is 90 degree. Your theta would be 90 degree. When this is 90 degree, the shift in the wavelength would be exactly h over mec, and this we call the Compton wavelength. So that is it for Compton scattering. Now we gonna move on to the particle wave duality. So the particle wave duality was first proposed by De Broglie when he said that a photon can behave as a particle with momentum and energy, so E and P. But it can also be a wave with frequency. With a frequency. And from this, he discovered a property which is universal, that is the matter waves. So he said that the particle wave duality is universal. Remember this. And he called this property matter wave. So matter waves are just probability amplitudes. And with a wave with momentum p, you get a plane wave that has a wavelength equal to h over p. A plane wave with no potential pulling it down, with momentum p. And that is it. So next we're gonna speak some about the double slit experiments. I believe this was first done by Germer and Davidson. So what happened is that they shoot a beam of electron through a double slit into a screen, and they expected for it to behave like particles. But as we know that electrons are quantum objects, so what they get instead is a lot of dense and then scarce and then dense kind of sort of stripe-like pattern on the board that they shoot the beam through a double slit. Shoot a beam through the double slit, and they would get it on a board of sorts. So what they get is that the stripe pattern that is exactly like waves. So normally you would think that it would just condense at these two places, but what they get instead is that there is interference happening here. And later on, when scientists try to put like a detector or a measurement of sorts around here, they get this. It is kind of concentrated here, and they ask why. And from this question, they get the particle wave duality, but the wave only collapses when it is observed. So in other words, you can say that wave function in quantum mechanics would collapse into localized solution when observed. So they behave kind of differently when observed and when they are not. So that is where the particle wave duality is sort of derived from. And I guess that's it for today. Goodbye.